Welcome to the 2023 Loeb lectures. We're happy to have Asimina ARVANITAKI here as our Loeb lecturer, giving talks today, tomorrow, and Wednesday. Mina is the Stavros Niarchos Foundation Aristarchus Chair in Theoretical Physics at the Perimeter Institute, where she has worked since 2014. She got her PhD at Stanford in 2008, working with Savas Dimopoulos, and then she did postdoctoral research at Lawrence Berkeley National Lab and at Stanford. Mina is a particle physicist. She designs new experiments to look for physics, new kinds of fundamental physics beyond the standard model. A lot of the work that she does relies on making use of new developments in metrology, things like atomic clocks, applying AMO techniques to searching for new kinds of particle physics. She's worked on a variety of topics in theoretical particle physics, including things like split supersymmetry, lots of developments in axion physics. She's pioneered new ideas about getting high precision searches for spin-dependent forces of the sort that might arise, for example, from axions and axion-like particles. Mina has won several awards. Let me just mention a couple of them. The 2016 Early Researcher Award from the Ontario Ministry of Research, Innovation, and Science. And in 2017, she was a winner of the New Horizons Prize from the Breakthrough Prize Foundation. And today, Mina is going to be telling us today and in the next two lectures, Mina is going to be telling us about some new work reassessing the cosmic neutrino background, which has overturned some kind of conventional wisdom of a few decades about why doing certain things is not a good idea. Turns out some of that wisdom was flawed. So we're happy to hear from Mina.
Thank you, Matt. Thank you. It's a great pleasure to see you all. It's a true honor to give these lectures today and tomorrow and on Wednesday. I'm particularly excited to be giving these talks. First of all, because they are not going to be review talks. So this is work that is basically brand new. The last paper on the series appeared something like 10 days ago. And it's actually work that I'm really excited about, okay? And as Matt foretold, and probably read from my abstract, it has to do with a cosmic neutrino background, okay? And its prospects to detect it in a laboratory setting, essentially. Now, in order to, before I go there, I need to tell you a bit about what it is. And to do that, we have to go either way back and give you a brief history of what we understand about the universe. So we believe the universe was created out of a Big Bang, a hot soup. We don't really know what the initial temperature of that hot soup was. We think it's quite high. In principle, experimentally, we know it has to be hotter than an MeV. And as the universe expanded, this hot soup cooled down. And as it cooled down, it went through several stages. For example, in the beginning, when it was super hot, quarks were unconfined. Eventually, nucleons formed, then nuclei formed, and as the universe cooled even further, atoms formed, and photons started propagating freely in our universe. And what we know today, that through the galaxies and the size of the universe, we know that it's a structure that's roughly 10 billion years old. A great thing about this picture I would like to point out is a landmark point is the creation of the cosmic microwave background. This is the time where atoms formed and the universe became transparent to photons. This was when the universe was around 400,000 years old. And it's a very special time because it allows us to actually take a picture of what the universe looked like. And this is a picture from the Planck satellite. It told us quite a lot. In fact, it changed the first picture of the CMB from COBE, changed the way we understood the universe back in the 90s. Today, continuing observations of the cosmic microwave background, or the CMB as we most we call it, turned the CMB into a cosmology, into precision science. We know what the universe is made out of with 2% precision, which is amazing if you think about it. But just doing satellite, basically laboratory observations. So the cosmic neutrino background is a similar thing. The cosmic neutrino background is another relic from the Big Bang. It's the time where these particles called neutrinos became the universe became transparent to neutrino particles. Okay, it happened when the universe was a fraction of a second old, not 400,000 years old, but a fraction of a second old. Okay, and just to bring everyone on the same. I don't know if there are students here that may not know that neutrinos are partners of the electron that have no charge, and they only appear in radioactive decays. So they interact what we call the weak force, which is what Fermi became famous for. Okay, and over the years they have they've been the center of attention. The latest of which, a fellow Canadian, MacDonald, got the Nobel Prize for his studying the basic properties of these particles. So these relic neutrinos are neutrinos from the Big Bang that were created, as I said. The universe was a fraction old. They have very special properties in the standard cosmology as we know it. They follow a Fermi-Dirac distribution, thermal distribution. They have a temperature of about 2 Kelvin. It's slightly smaller than the temperature of the CMB photons. They have very low momentum. They're extremely slow, and there are very few of them in a centimeter cubed. In fact, you have roughly 56 per centimeter cubed per species of neutrinos. Okay. Now, depending on the type of neutrino. And we know from the matter-antimatter asymmetry that we observe in baryons that you expect that the neutrinos and antineutrinos have the same number, roughly in 1 part in 10 to the 9. Okay. So this is what determines the standard model expectations, and these are the rough properties of the cosmic neutrino background. So it is important, because if discovered, it would push our knowledge of the universe to the earliest possible that we will have data for. Okay. The other thing why it is important is that neutrinos are the least known part of the standard model. They have 3 flavors. There are 7+ parameters associated with them. So they are still under a very active field of research. But contrary to the cosmic microwave background, contrary to the CMB, the CMB has been extremely hard to see. The CMB we actually discovered in the 60s, and we very quickly started doing experiments on it and observations on it. But neutrinos are different. The reason is photons interact strongly with us. Neutrinos interact with a weak force, so they don't interact much. So if one tries to calculate the cross-section, which is set by G Fermi, what you will see here is the Fermi constant. It goes like the Fermi constant square, the scattering rate, which is extremely small. In fact, you know that if there's something that decoupled from the expansion of the universe at a time where the universe was 1 second old, it basically doesn't interact at all. It goes through everything without interacting, okay? And the reason is mainly because they're so cold. They don't have enough energy. Now, people have found ways to kind of enhance that rate. The first paper appeared in '62 by Weinberg, where he noted that the interaction cross-section of cosmic neutrinos, these relic neutrinos, can be enhanced when they are absorbed in radioactive decays. So, for example, take a tritium nucleus, it can absorb a relic neutrino and convert to a helium-3 and an electron. Okay, so that's a huge enhancement in the cross-section. And there is the Ptolemy proposal that tries to look for this extremely rare process on top of the usual decay, because tritium decay with a usual radioactive decay. It will decay to a helium nucleus and antineutrino and an electron. So that makes the fact that you have to distinguish your signal over this huge background is what makes this experiment worthwhile, but also challenging. Another way to do to enhance that cross section is through coherent scattering. Okay, because these are very low energy, when they scatter off material, their momentum transfer is so small that they couple coherently over a millimeter size object. Okay, and that can give a boost to the cross section. Again, though, that cross section is still extremely small, far away from anything we have seen. So there is one more way in which these neutrinos interact, and that's through refraction. And refraction is proportional to the coupling, not the coupling squared. Refraction, you know, from photons, from optics, you know, lenses, but in fact, everything refracts. Neutrons refract. Fermi himself was doing experiments with neutrons, and there are some beautiful papers, declassified papers, if you Google, where he was playing around with how neutrons reflect. Electrons refract, okay? And as a result, neutrinos refract as well. So people thought that that they could kind of detect the effects of refraction as neutrinos go through material. So you see here in a prism, you shoot a beam of light and you see it bending. So during the bending, it changes its momentum. So that means that the prism has to have recoil against that change of momentum in the beam. So people said, okay, let's look for this refractive change of momentum of neutrinos. And in fact, you can understand this even further if you think about the fact that due to the weak force, every atom that sits in the neutrino C feels an interaction potential U that's proportional to the Fermi constant, the weak charge of the atom, and the difference between neutrinos and antineutrinos. Okay. Now the process of detecting the bending of neutrinos as they go through a prism or an object or an extended object, if you like, is equivalent to saying, can I detect the force that's produced by this interaction potential, the grad U? And in fact, back in the 70s, people wrote quite a few proposals and started designing experiments to try to detect this force. Still very small, but slightly bigger than the effect mentioned before, perhaps. Unfortunately, people realized, well, if I take the grad, this energy density, it depends proportional to the gradient of the density of neutrinos. So if you have a uniform neutrino density, there is no force. And you can see this if you think about beams of neutrinos or particle neutrinos reflecting from a prism, is the fact that neutrinos come from all directions. So the kicks will average out to zero. So there is no net force. And this is the essence of no-go theorems that appear in 82 and basically stop all these proposals on their tracks. There is one proposal that survived and one effect that survived these things, and it has to do with interaction of neutrinos with polarized matter. So if I take a spin, an electron spin or a nuclear spin, and I put it in a sea of neutrinos, there's going to be a small energy splitting between the state pointing up or pointing down. This energy splitting is extremely, extremely tiny. So it's 10 to the minus 47 eV, which is much, much smaller than anything we have detected in a laboratory setting. It's more than 20 orders of magnitude. And in fact, it's so small, gets an additional suppression of this small neutrino and antineutrino symmetry, which I told you is 1 part in 10 to the 9. Okay. So what I will discuss now is in fact something that relies, again, it's a refractive effect that gives a very easy way out of these all no-go theorems, and tells you that the Earth itself creates a local gradient of the neutrino asymmetry and enhances that asymmetry due to reflection. So the reason that happens is pictorially given here. So up we are outside the Earth, and then we are inside. Because of the way neutrinos interact, if you have electron antineutrinos, we have three types of neutrinos, electron, muon, and tau neutrinos. Turns out electron antineutrinos, muon, and tau neutrinos are sped up as they go through the Earth. So if you draw them as rays, they move away from the surface, while neutrinos and muon and tau antineutrinos are slowed down. So if you draw them as rays, they get pushed towards the surface. Eventually, once they come closer to grays and infinitely, essentially they start reflecting. So it's this slowdown of the neutrinos and of electron neutrinos and muon and tau antineutrinos that creates an excess of their density on the surface of the Earth. Okay. And now we'll go in detail to see how that comes about. So I talked about this interaction energy of an atom when it sits when it sits in the neutrino background. That interaction energy is exactly related to the index of refraction. So if I define the index of refraction difference from 1 as delta nu, and this is inspired by X-rays, and I'll tell you a bit why, it measures basically the change of kinetic energy of neutrinos outside the material versus inside. Okay, so it goes like the mass of the neutrino times the energy, interaction energy, divided the momentum squared. And there's a minus sign that tells you that things that have a attractive potential, the index of refraction is larger than 1. Things that are repelled have an index of refraction is less than 1. Yeah, question. Yes, roughly. Why does it seem weird? Good. So there are small differences. So there is a small difference that has to do with flavor. So they do decouple slightly different times. So, but that for my purposes, this doesn't matter. Okay. And what matters more is so in the end result depends when I write nu minus nu bar is the difference between things of the same flavor. So the 10 to the minus 9, even if you have more electron neutrinos, that means you also have more electron antineutrinos. Okay, so overall it won't. Does that answer your question? Yeah. Yeah. Thank you for asking, and please do the same. So that index difference of refraction is different from 1. You can plug in numbers for things like a rock or metal. It ranges for anything between 10 minus 8 and 10 minus 7. This is very similar to the index of refraction of X-rays. Okay, so people have seen this index of refraction before in optics, and that's why we call this quantity delta, inspired by X-rays. So this interaction potential, as I said, depends on the type of neutrino you have. And it becomes bigger. This raw matter tells you that it becomes bigger for denser material, like iron. And it becomes bigger for things that have a lot of neutrons. So big nuclei, like uranium, tungsten, gold. And if you plug in the numbers, you will see that there is an interaction that's, as I said, it's repulsive for, the interaction is repulsive for electron neutrinos and muon and tau antineutrinos, okay? Just to give you an idea of the interaction energy U, you can see here that compares with 10 to the minus 15 to the minus 13 versus the kinetic energy of these neutrinos. So, yes. Before, yes. Oh, yes. So before you said for the Stodolsky effect, there was the relative velocity of the neutrinos. Yes. No, I mean, they move pretty fast already, right? The question is, can you enhance the relative velocity of neutrinos? The neutrinos move with 10 to the almost 10 to the minus 2 of the speed of light, 10 to the minus 3. It's pretty, they move. Oh, yeah, we can discuss that later. But yeah, hold that thought. I mean, yeah, we had crazy thoughts like that, but it won't give any signal that we care about on Earth. Just so you know, like, and I'll come to that because it's actually a fact that happens anyway. So how do we understand this? So index of refraction tells you have a wave that is incident on interface between two material, and then I have to take the part that the incident wave, and then I have the reflected wave and the transmitted wave. Now, because we can correlate this index of refraction to this interaction energy U, we can reduce the problem of interacting of neutrinos with the Earth to waves interacting with a square well potential that we know from quantum mechanics. Okay, so if you see it as a 1D problem, so you see here at the bottom, this is the energy, typical energy of the wave, and see you have the little step is your potential well. So let's look at the ones we care about, are the ones that are repelled. You see that most of the ways, the typical energy, you have an incoming wave, you have a reflected wave, and then a transmitted wave, but most of those waves just go through. The effects of reflection transmissions are really small. Now, if you go to neutrinos whose energy is comparable to this step, you will see that they don't have enough energy to penetrate, less energy than that step. They don't have enough energy to penetrate, okay? So far, by the way, I'm treating the neutrinos as a 1D problem, okay? So if you hit the step and then you bounce back completely, but because we are waves, we know there is gonna be penetration in the classically invisible region, which is known as the evanescent wave, okay? So this reflection is exactly what gives us, this evanescent wave is eventually what will determine the gradient of the neutrino density on the surface of the Earth. Now, as I said, so far, we've treated the neutrinos as a, we've treated the neutrinos as a 1D problem. But of course, there is 1D, we have 3D, neutrinos are coming from all directions. And for the time being, let's assume that the Earth is flat, okay? Which for local purposes it is, okay? So we have neutrinos hitting from one side at an angle, and then they reflect back and there is some transmitted wave. Now here we have to take into account the symmetries of a problem. So because there is translational invariance in the perpendicular direction, what matters for the dynamics is the momentum. What matters in the dynamics is only the momentum perpendicular to the surface. The momentum parallel to the surface is preserved, remains unchanged inside and outside. So all the dynamics are determined by how much momentum the perpendicular to the surface the neutrinos have. So in order for total reflection to occur, you need this total momentum, the kinetic energy in the perpendicular direction to be less than the interaction potential. And then now you see that the critical momentum for reflection is related to the square root of the interaction potential, which is proportional to the square root of the coupling constant. Okay? And if you plug in the numbers for the Earth, this scale is roughly 3 meters, which is very different from cosmological. Usually, when people talk about gradients of densities of dark matter, or they talk about megaparsec, kiloparsec scales. This is 3 meters. This is laboratory scales. Okay, all this because of these refraction effects. Okay, and as I said, and that eventually leads to this excess, this reflection, this slowdown. So the incidence angle for which this reflection occurs defines the critical angle, and that's just the ratio of the momentum over of the critical momentum for reflection over the total momentum. And then when you plug in the numbers, you get a number that's 10 to the minus 4. Yes, question. 3 meters is the scale of the gradient. See, because, okay, I should be careful because I work in units where H bar and C are 1. I'm a particle theorist. So momentum for me has units of inverse length. Okay, so you can think about it as a, let's call it as a de Broglie wavelength. Okay, so this is roughly 3 meters. That's the scale. So this momentum perpendicular corresponds to the Broglie wavelength you can think about of roughly 3 meters. Does that answer? Yeah. Yeah. Yes. Yeah. Yeah. I mean, they're flying all the way. I mean, in your fingertip, you have 50 all the time. In your fingertip, centimeter cubed. So your fingertip has 50 neutrinos of one type all the time. To create like to trap them. Okay. Yeah, we thought about that. Like, okay. Yes, exactly. So we actually, okay, now we're going to the crazy idea. So we've been thinking about this a lot. One of the first things we thought about was exactly this. Actually, we thought about designing optical fibers for neutrinos, where you have them come in and they get trapped and they bounce around. Turns out you cannot do better than 10 to the minus 4. And the pesky little reason is because there are several things, and ultimately, I don't think they will work for another reason, but neutrinos are fermions. So it's not like photons where you can keep piling them on. There is Pauli's exclusion principle. So it turns out when you calculate the maximum density you can get in an optical fiber, for neutrinos, it's not much different than 10 to the minus 4 times their nominal density. Because you have to trap them right, there is there's the mode size that you need, which is roughly 3 meters. Yes. The other reason that we don't think this will work, anyway, you can understand what rabbit hole we went under. So into now. So the reason that it doesn't work, there's something about optical fibers. So basically, if there is any sort of bend on the optical fiber, these things won't stay because the interaction potential is so small that they escape. So the mode is not well trapped. It's not well localized. So it's very easy for them to escape anyway. So the local thing that the Earth does for this storage thing, there are maybe other things you can do with reflection. We can discuss them actually later in the talk. But yeah, but yeah. Anyway, good question. Yeah, there is a, yeah. So the Earth actually is kind of an ideal setup. Yeah, you have a question? Yeah. Sorry, say that again. So the densities goes like the square root. So the density that I'm assuming here to give you the 3 meters is basically the density of silicon oxide rock. So it's the square root. So it doesn't change much. Like, yeah. Thank you. Yeah, keep coming with the questions. Love it. Okay. Oh, I could repeat the question. So the question is, well, how does it scale with the density? And it scales like the square root of the density, this effect. So the amount of neutrinos that you get is the excess, the fractional excess of the ones that are traffic jam versus the one that just plow through. It's about 10 to the minus 4. Okay. which is much bigger in scales with the square root of the neutrino mass. And the other thing is, this is 5 orders of magnitude larger than the naive expectation, that the standard model expectation, the 10 to the minus 9. So already the presence of the Earth drastically modifies just the fact that the Earth is flat locally is enough to change this distribution. Okay. And the gradients set by the velocity, the momentum perpendicular to the surface, which also sets the evanescent wave scale. So this 3 meters. Okay. And this is essentially the summary plot for this. So on the vertical axis, you have the density, units of this 56 per centimeter cubed that you expect for neutrinos. And then you see the distance from the Earth's surface. You see one side is outside and the other inside. You see the gradient due to the evanescent wave. And this plot, you see for different masses, the big change that happens for point A TV is that neutrinos cluster a bit in our local galaxy cluster. So that gives you a bit boost of the density. So it gives you a bit of an enhanced signal. But I think, though, honestly, I think this value is very optimistic because it is favored by cosmological data. Okay. So summarize, we believe neutrinos coming in create this fuzz around the surface of the Earth, roughly 3 meters in size. And it tells you now that all these no-go theorems that you thought were there before are trivially no longer apply for the Earth. Yes, John? Yeah, that's an excellent question, John. That's an excellent question. I think the minimum size of a flat patch you need, if this is where you're going at, is roughly kilometer size, because you need to see how, what I didn't talk about is neutrinos come from the behind, right? I mean, they're always going to be there. And as long as the Earth is flat enough within a kilometer, that won't happen. And I'll talk about it more tomorrow. Excellent. By the way, no one ever asks about neutrinos coming from behind, because I always never talk about it, but they're always there. They come from behind. Anyway, great. So the question is, though, can we do better? Okay, as you asked back there, it's like, can we trap them? Can we do something interesting with them? And we went back forth many ideas, and the thing we think will help is something that looks like this. So something that looks like a sea urchin. So you take rods that have a width W and a length L, and you put them radially on the surface of the sphere R, okay? And eventually, this is a setup that relies solely on the wave nature of neutrinos, okay? Neutrinos, everything's a wave. And turns out they have a wavelength that's roughly 2 to 4 millimeters. And we think this is a diffraction gradient. I'll explain to you how it works briefly. That will give an enhanced asymmetry at the center of the structure. Okay, so let's see how that works. So let's take a rod. Now it has 3 Ds, but let's make it 2D. We have a width W and a length L. Let's take a wave, a neutrino wave, that hits it paraxially, parallel to the axis of symmetry of this rod. As the neutrino goes through, the neutrino wave goes through, at the end of this rod, to a very good approximation, yes? Okay, let me try to see if I can remove it more. Hide. Plot meeting controls. Yeah, okay, thank you. So at the end of to a very good approximation, the neutrino wave at the end of the rod will be outside the rod. It will have the same e to the minus ikz. It will still be the usual plane wave that you throw on it. But on front of the rod, on the facet of the rod, width of the area w squared, it would have acquired an additional phase because it propagated through matter. And the additional phase that it acquired is the propagation difference in the propagation phase it has from propagating inside and outside. So the phase is the momentum k, the wave number k, the difference of the index of refraction from 1 delta times the length of the rod. Okay, that's why we're saying that the rod is a neutrino phase diffractor, because it imprints a phase on the neutrino wave at a place where you want it. It doesn't do it uniformly across the facet of the wave. And this is very important, okay? And the bottom line is, after you propagate the wave from the end of the stick to some distance away, you will see now that because the phase is exactly opposite in sign for neutrinos that have delta nu larger than 0 and delta nu less than 0, it turns out you can create an excess of neutrinos that have delta nu larger than 0 a certain distance away. And what is the distance and what determines it? The reason this happens is because the wave essentially interferes with itself. It diffracts with itself. So the wave from the plane wave that's left intact interacts with a part of the wave that went through the opening of the stick. And and the other thing is that, if you remember, and I'll talk more about this on Wednesday, there is Hoyle's principle. You have partial waves from the front of the stick. These partial waves will add up coherently a certain distance away. That distance is set by the width squared divided by the wavelength of the neutrino. Okay? And that excess will persist further away. It just drop linearly with a distance. So this interference effect causes a difference in the distribution of the wave is a certain distance away from the stick. This is pure wave dynamics. Okay, if I were to take the wavelength of the neutrino to 0, this distance will go to infinity and I will have a 0 effect. Okay, if you do geometric optics on this, you will see that if you draw rays, you will see that the rays don't bend. So it's only pure, it's a pure wave effect when this happens. And the figure of merit, as I said, for this effect to be maximized, this interference to be maximized, you need to put your detector, let's say, to see the maximum difference between neutrinos with delta nu larger than 0 and delta nu less than 0, is to put it at a distance, the width squared over lambda away. And the width of the pattern, this excess, is roughly W, set by the width. Okay. So now, this is actually a more fancy plot of this. So this is where you take, again, the same paraxial wave as a function of, and you see the asymmetry as a function of the distance from the stick and from the rod. And here I took a length of the rod that's 10 meters and a width that's 17 centimeters. And you see that the maximum, as I said, appears at a distance roughly W squared over lambda. It drops off linearly after that. And this is another cross section in the direction of propagation like this. And the width of that is still W, and it actually, sorry, the size of the spot, as you move further away, grows like the square root of the distance, because it's diffraction, right? If you have, if anyone remembers their optics class, if I have light scattering from an opening, this is the same rough properties it has, okay, for the bright spot. So, of course, neutrinos, first of all, they are not monochromatic, okay? And And you have to average over, you integrate over the momenta that they have. They have a thermal spectrum. So when you do that, and you have the same paraxial wave hitting the rod, you find actually that the symmetry persists. For people that are more accustomed in optics, if you think about this rod as an optical element, is the worst optical element you can have. It has horrible color aberration, it has astigmatism, all the bad things, but you don't care, okay? We just do want to make not necessarily big differences. So now, of course, the other difference with neutrinos is that not only are they not monochromatic, they come from all directions. Yes, question? Okay, good, excellent. So that's a very good question. You don't, because these neutrinos are super cold, so they don't oscillate anymore. And this is a key point. Thank you for asking. So because, yes? Don't do your horses, okay? Just wait. Let's explain, and then I'll come to the type of detector. So because neutrinos are coming from all directions, now you see that we have to put the sticks on the surface of the sphere, essentially. So this is how we came up with this sea urchin-looking structure, okay? And in order to maximize the effect of each one, you need to put the center of the sphere at a distance w squared over lambda. Now, most of the time, the neutrino wave will come in between the sticks, and you need to do a similar calculation that we did before for the case where the neutrino comes in between the sticks, and you get an asymmetry that kind of looks like this, okay? So now you need to average over the incidence angle, okay? And then we need to pick, after picking lambda, after picking the length L of the rod, R turns out has to be roughly of the same size to maximize the, to make sure that even when neutrino rays come in between the sticks, the effect is big. They get modified by quite a bit. And then we need to choose the width so that W squared over a lambda neutrino is roughly the size of the radius, okay? And this is where we come up with these parameters, okay? We came up with things that have, we don't want to scare people. People can go as big as they want. They can make this a kilometer if they want. We pick something between 2 meters and 100 meters because I think this is realistic to build, okay? Great material for it, actually my favorite, is depleted uranium. It's better to use for this than ammunition, okay? So it turns out it creates a huge effect. Of course, great material that are not slightly radioactive is tungsten, and of course iron, because it has high density. So these are the parameters of the things that we discussed, and we picked 3 different things: 2 meter, 10 meter, and 100 meter, with different with a width optimized, and there's a slight gap between the sticks just to maximize the signal. Doesn't matter much. And this is the type of asymmetry. So if I were to take a cut across the center of the structure and measure my asymmetry, this is the type of signal I would see for the 3 different setups: the 2 meter uranium, the 10 meter tungsten, and 100 meter iron. And let's go to the 100 meter iron, for example. You see that I get an asymmetry. The size of the asymmetry depends on the type of the neutrino I have. Depends on the type of neutrino I have. And you see now that I get an asymmetry that's roughly more than 10 to minus 2. Remember, the asymmetry that we started with was 10 to the minus 9. Okay, this is a 7 orders of magnitude enhancement. The other interesting thing is that you have created a gradient now. That's not 3 meters. It's actually of order 10 centimeters. Okay. So this is where we come to detection, okay? So, and we've created, we think we have a structure that can significantly manipulate the local density of neutrinos. So question is, how do you detect it? And we don't have a proposal for that. The reason is because we decided to first think about what is the size of the signal that we're trying to detect. How big can we make that? And then we think of an experiment. So we call it the principle of factorization. But I will talk about the possible detection scheme, okay? So what you would do is if you take, for example, a 10 centimeter tungsten mass and you put it around the center of that structure, our sea urchin, you will see that it will feel a force, okay? That force, and if you can see it there correctly, it's 10 to the minus 28 Newton. It's tiny, okay? So this is roughly 8 orders of magnitude away from where experiments are right now. Now, and this is kind of a summary plot. Of course, that force depends a bit on the mass. And as I said before, it depends a bit on the clustering of neutrinos. So for heavier neutrinos, this can be bigger. Now, just to give you an idea of what can be achieved. Right now, these experiments that could be used for this, and I will discuss them more again on Wednesday, they are far away from the standard quantum limit, okay? But if you imagine that there are different ways you can do it. You don't really have to cool down to the ground state. There are different ways you can do it. If you calculate the standard quantum limit for the 10 centimeter tungsten mass, you will find that it's kind of comparable, given some parameters loosely inspired by current experiments, okay? And this would be kind of like the force sensed by, if I treated the mass as a harmonic oscillator with a trapping frequency that's roughly a fraction of a millihertz, okay? But as I said, you should take this as indicative. This sets the target for experiments. I'm not proposing an experiment, just to be clear, because proposing experiments in a whole different ballpark. Okay, but at least now, before there was even a question, you were orders of magnitude away from whatever the standard quantum limit is. So at least now we can start having a conversation about, okay, what type of experiment can we actually build to detect this type of signal? Okay, so turns out that this setup can actually look for dark matter as well. Okay. The type of dark matter that is, we didn't scan all the dark matter candidates that are possible, but we picked one that we thought was more motivated, okay? So, and this is a dark matter candidate that's related to electric dipole moments. So electric dipole moments, probably in Harvard, I shouldn't talk much about electric dipole moments. You have John here, he can tell you all about them better than me. But just to summarize, they violate fundamental principles, the fundamental symmetries of nature. They're parity odd. So if you have an elementary particle with a magnetic moment and an electric dipole moment, and you apply parity, you take r to minus r, you see that the magnetic moment doesn't change, but the dipole moment does. So the particle changes under parity. So that means an electric dipole moment violates parity symmetry. If I take now time reversals, if I take t to minus t, you see now that the electric dipole moment remains unchanged, but the magnetic moment flips sign. So the particle changes, okay? So a fundamental electric dipole moment, a particle violates parity and time reversal, or people sometimes call time reversal symmetry CP, charge and parity symmetry, okay? And in the standard model, charge and parity or time reversal is not a good symmetry. We know it's violated. So people expected that there should be an electric dipole moment for the neutron. And it would arise through the presence of such a term. This is a term, this is a term that mixes the electric field of the strong interactions and the magnetic field of the strong interactions. And if present, it would cause an electric dipole moment for the neutron. its effects are parameterized by that theta parameter there. And the expectation was that the theta parameter was order 1. And we haven't found it. And this has been a problem for a while. The only thing that we managed to do is constrained to be extremely small. So the solution that people proposed back in the 70s and early 80s is to turn this theta parameter to dynamical field, which they call the QCD axiom. The moment you do that, the value of theta cosmologically naturally relaxes close to 0, and you get a very small electric dipole moment for the neutron. So this axion has an extremely small mass, and gets its mass from non-perturbative QCD effects. And its properties are determined by this decay constant effect. Okay. Now, turns out it's an excellent dark matter candidate. And if this decay constant is anything between 10 to the 8 and 10 to the 10 to the 8 and 10 to the 10 GeV, its wavelength is roughly between a fraction of a centimeter up to a meter. So you can imagine that the same, with slight modifications, the same gradient that we use to affect the structure of the cosmic neutrino background can be used to diffract locally this QCD axiom. Okay, and it produces a force. This is a plot that gives rough sensitivity based on this naive quantum limit that I showed before of the axion decay constant as a function of its mass. The blue is the QCD axion line that we talked about. And the interesting thing, this is actually much bigger than the one I calculated for the cosmic neutrino background. In fact, dark matter could be a background for this cosmic neutrino searches. Okay, so to conclude, I think people back in the 70s and 80s quickly gave up on fundamental properties, on studying refractive properties of elementary particles, of these weakly interacting particles. And we believe that the mere presence of the Earth is enough to significantly modify the distribution of the cosmic neutrino background on its surface. And we think you can actually create structures to drastically alter its distributions in a laboratory setting. And of course, this sets a challenge of experiments. And as I said, it turns out that these experiments appear to be roughly 8 orders of magnitude away. And this is the time where we go down memory lane and we talk about clocks. Okay, atomic clocks are a current standard of time. So a very naive way to understand how accurate they are right now is if you have a wristwatch, a quartz wristwatch, by some measure, it loses 1 second every year, by some measure, okay? This is the frequent stability. If you compare this to an atomic clock, the best atomic clocks now lose by the same measure 1 second every 100 billion years. This is 10 times the age of the universe, just to give you an idea how stable they are. But as you see, this is a plot that shows this fractional stability as a function of time. And it took a while to get there. Okay. The great thing about this, though, it took a while, but it's exponential, right? This is a log scale, the vertical axis. Another great example of this is, of course, EDM experiments. Similar thing. They actually kind of follow the same trajectory, and it's no accident. But we are 10 orders of magnitude for the last 70 years. Okay. And finally, there is one thing for particle physicists, what actually happens much faster, and that's WIMP searches. Searches for WIMP particles as dark matter have actually improved over a period of 30 years. Okay, and even though this plot that you see here is from 2012, I couldn't find a more recent one. It shows you, so you see here, they project down 10 to the minus 48 centimeters square, 2020. This is where experiments are now. They are doing this. This is like the neutrino floor, not the cosmic neutrino floor, another higher energy neutrino floor. It's really impressive. Okay, so bottom line is we set a challenge, and I don't think it will happen tomorrow. Okay. And ultimately, what I'm personally excited about is that if we were to detect the cosmic neutrino background, which is a fundamental ingredient of the standard cosmology, we may take a picture of the universe when it was just a fraction of a second old. Okay. So who knows how that looks like? That would be really cool. So thank you very much. Yes, Alex.
Thank you, Mina, for the great talk. Is there a directionality here on Earth to the neutrino background because we're moving through the galaxy? And if so, how does that affect the silicon structure?
The effects of this, that's an excellent question. Thank you. We haven't really calculated because these effects are small. So the variation of the signal due to the, of course, if you do the Stodolsky effect, it's maximal, right? Because you care exactly about VREL, the relative velocity. But the changes in the density that we talk about are small. We're talking about percent level, I think. Change.
But you're assuming.
I'm assuming isotropic.
Right.
It's not a big effect. It won't change what I talk about by much.
Okay.
Okay. And someone should calculate. The bottom line is that someone should probably sit down and calculate. I haven't, it's my to-do list. I haven't done that yet, but it's not a big effect. Yes. Yeah.
So if we could actually detect these cosmic neutrinos, what kind of questions of cosmology could we probe, and how much further could we go from what we already know from the CMB?
Yeah, so the CMB is at 400,000 years, right? So these were generated at a fraction of a second. So in principle, I could tell you the very nice thing, we go back to 1 second versus 400,000 years, okay, which is a huge, huge change. In reality, though, we do have some knowledge of the universe when it was about 1 second old, and that has to do with something called the Big Bang nucleosynthesis. So that we know from measuring the primordial abundance of basically hydrogen and helium, the relative fractions, we have some idea of roughly what happened at about a second. But these neutrinos were formed beforehand, okay? So this will take back, and in fact, Big Bang nucleosynthesis, the fact that we have that information is a powerful probe. Anyone that works on particle physics and tries to do cosmology with a new model, you get tons of constraints from it. So I don't know exactly what it will look like, but it will take our knowledge further back, a bit back than what we already know.
But are there, I guess, any specific questions you're interested, like inflation or?
No, inflation probably it could tell us a bit about Thierry heat or probably the degrees of freedom that were in thermal equilibrium at the time. It may tell us a bit, I don't know, about sterile neutrinos, perhaps, if you want to go beyond the standard model physics. But I don't know. We'll see. It's hard to predict what something will show you when you haven't seen it yet.
Thank you.
Thank you.
So back to my question about the 3 meters and the density. On a galactic scale, you have some gas which is really dilute, but
yeah,
scales are much larger. So can I think about neutrinos reflecting on our galaxy on galactic
No,
scale
no.
getting less, or
No, I think that's tiny.
it's tiny?
That's tiny. I mean, the densities are really small.
Yeah, but
The
distance is
biggest
large.
thing, yeah, the distance, well, it doesn't matter, right? Because in fact, I mean, inhomogeneities will mess that up. And that's why I was telling John that you need like a flat surface. I mean, the galaxy, for example, if you want to think about the best thing is a neutron star. A neutron star will give you order 1. Like neutron star does like changes this by a lot, if you think about it. So so yeah, I don't think galactic, it's just too dilute to do anything like I think interesting. I mean, it's worth thinking about. It's just too dilute. Talking about tiny interaction energies. So the fraction of the things that will be affected is really small. More questions? Thank you.